Uh, Good evening, everyone. So today I am going to discuss the week 6 assignment 6 of the previous year assignment. So okay, uh, so uh, yeah, so this is the course of Basic Electronics NOCEE62, and I am taking the NPTEL tutorial class. So myself is Subhajit Basak, PMRF Scholar at IIT Bombay. So far we have discussed from week 1 assignment to week 5 assignment of the previous year, and now today I am going to discuss about the assignment 6 of week 6. So let's start. So here in the first problem, it is said like let A1 be a common emitter amplifier with the resistance RE completely bypassed. So at first I will like to draw what is the configuration of a common emitter amplifier as we have discussed in the earlier class. So suppose there is a source which is VCC, and from there we have some voltage divider which is R1, and then we have R2. So this is R1 and this is R2, and then some AC input signal which is the source signal. It is a small signal Vs which is applying across the input terminal. So here we put a coupling capacitor which is nothing but CB. In the base side, in the base terminal, we put a coupling capacitor. So so the coupling capacitor basically blocks the DC input uh, uh, to feed into the source AC input signal side, and also it helps to put pass the AC signal in the base terminal of the transistor. So there is a transistor. So here we have RC, that is the collector resistance, and here again we put a coupling capacitor which is nothing but CC, and across it we put a load which is RL, nothing but RL, and here we put a emitter resistance, this is RE. But due to this RE, the stability becomes an issue, and so that we use a bypass capacitor to bypass the AC signal, so that there should be a larger amount of gain. So the gain, here the gain refers to the small signal gain. So because of RE, actually due to RE, the small signal gain becomes less. So to bypass that, we use this bypass capacitor, so that the entire VB, the small signal VB, can come across this side, and there will be no drop in the RE, and as a result we can have a larger amount of gain. So this is the basic configuration. This is VCC. Okay, yeah. So this is the basic configuration of a common emitter amplifier. So here in the question it is discussed, let A1 be a common emitter amplifier with the resistance RE completely bypassed. So this entire amount of RE is bypassed by this bypass capacitor CE. Okay, so this is A1 amplifier. Okay, and let A2 be the same common emitter amplifier with the same configuration. Just the difference is that this RD is divided into two parts, which is RD1 and RD2, where RD2 is bypassed but RD1 is not bypassed. So if we draw the second circuit, so here we have R1, here we have R2, and then we have this NPN BJT, this is RC. The rest of the configurations are similar to configuration of A1. Okay, CB, and here we apply a small signal which is nothing but Vs, and here the RD consists of two resistance which is RE1 and RE2. Okay, yeah, and here it's VCC is applied. Okay, so here is another coupling capacitance which is CC, and here we apply a load resistance which is RL, and this RD2 is bypassed by using the bypass capacitor that is connected in the emitter side. Okay, so this is the configuration of A2, common emitter amplifier with A2. So for A1, the entire resistance is bypassed by the bypass capacitor CE, and here in configuration A2, only a certain amount of RD, that is the emitter resistance which is RD2, is bypassed by this coupling capacitor CE. Okay, so is bypassed. The resistance RD of A1 is equal to RD1 plus RD2 in A2. That means this RD is equal to nothing but RE is nothing but RD1 plus RD2. Okay, yeah. So now all other parameters are identical in A1 and A2. So which of the following statement is true? So here are four options. So we will discuss all of this, and we'll see that which is satisfying, which option is satisfying for the above configurations. Okay, yeah. So at first we have to find out the input resistance, because here it is said like A1 allows a larger input voltage amplitude without causing distortion in the output voltage, A2 has larger input resistance, A2 has larger DC bias current, or A1 has smaller voltage gain. Okay, so we will draw the small signal equivalent model of both the configuration or both the circuit. So for A1, for A1 for A1 we are going to draw the small signal model, small signal model or AC model. Okay, small signal model. So for small signal model, so I have already discussed that how you have to draw the small signal model. So for A1, so this Vs is the source voltage that is applied. So here we have Vs, it is a small signal, so we denote it with small v. Okay, Vs is applied, and now this is the DC blocking capacitor, that is the coupling capacitor, but it does not block the AC, so AC will bypass this capacitor, right? So for AC analysis or small signal analysis, this capacitor can be act as a short circuit, right? Yeah, okay, yeah. So then from here we have two resistances, R2 is going to ground and R1 it is also going to ground, because VCC is a DC source and we are now considering the small signal model. So while considering the small signal model, uh, we have to make the DC sources equal to 0, right? Okay, so here we have R1, another resistance we have R2, and we have that amplifier model which is, here we have R pi, across that the voltage is V pi. Okay, yeah. So all of these things are ground. Now this thing is the emitter terminal, this thing is the base terminal, and this thing is the collector terminal. Okay, so from collector to emitter there is a current source which is nothing but GM V pi, so which is connected to the emitter. And from collector we can see, so this terminal is nothing but base, this terminal is nothing but collector, and this terminal is nothing but emitter. Okay, so from collector we have one RC that is connected to ground because VCC is ground, so we have one RC over here, RC, and then we have, so this is, there is also another coupling capacitor, so that will be again short during the AC analysis or small signal analysis. So from there we have RL which is connected to ground. Okay, now what is happening from the emitter, so this terminal is ground. Okay, and this terminal is also ground. Now the emitter here, for the AC analysis, this part acts as a short circuit because the capacitor acts as a short circuit small signal analysis. So this bypassing capacitor is short circuit, so that means this resistor, there is one path with this resistor and another part direct shorted to ground. So obviously the current will flow through the shortest resistance path, which is nothing but this short circuit path. So the emitter is, during AC or small signal analysis, this is connected to ground. Okay, so this is the AC equivalent model, small signal model of A1. Okay, so if we draw the similarly the small signal model of A2, then we get for the A2, the small signal model can be written as, so there will be Vs, similarly there will be R1, similarly there will be R2, and here in the emitter, so there is another resistance which is RE1, and RE2 is bypass, so RE2 is, we will not consider RE2 during the AC analysis. We will consider this CE, coupling capacitance, because it is connected to ground. Okay, so here is another resistance RE1, and here is R pi, uh, and this is the V pi, that is the small signal hybrid pi model, right? So here it will be again GM V pi, here will be again RC, and here will be RL. So the difference of small signal model between A1 and A2 is like, after this emitter terminal, so this is basically the emitter terminal, this is basically the base terminal, this is basically the collector terminal. So in this emitter terminal, R1 is connected before it goes to ground. Okay, so now how we can analyze this circuit? So if we consider this circuit, so we have to find out two different things, right? One is the input resistance and other is the voltage gain, that is the small signal voltage gain, or we can refer it as voltage gain, simply voltage gain. So one is input resistance, another is the voltage gain. So if we consider about the this input resistance, so for A1, for model A1, the input resistance, how we can find out? So to find out the input resistance, we just detach the Vs, that is a source, that is a source signal, and we attach a test voltage which is nothing but Vt, and we consider the some amount of current It is flowing from the Vt. So if we uh, calculate Vt by It, then that will be the input resistance. Okay, so we ignore the source voltages. So if it current is coming out of that, so the total resistance of, so for A1 the total resistance is R in is nothing but Vt divided by It. So we can easily see that the current is dividing into three part, and this three part is parallel because R1 is simply going to ground, R2 is also going to ground, and R pi is also going to ground. So here it will be R1 parallel R2 parallel R pi. Okay, okay. And in case of A2, the thing is little bit complex. That is, so here we have R pi. So suppose there is IV current flowing through this. Here we have IE current flowing, and here we have beta IB current flowing because it is IC current, collector current, right? So IE is nothing but IB plus IC, and IC is, as I have already written, it is beta IB. IC is beta IB, so it is beta IB. So it will be 1 plus beta, 1 plus beta into IB. Okay, so now how we can write? So IB current is flowing through this. So now this R in, for in case of A2, in case of A2, this I R in will be, so we will similarly add an test voltage VT, which is emitting current IT, right? Okay, so R input, nothing but R1 parallel R2 parallel with, so there it is IB current is flowing through R pi, and also it is 1 plus beta IB into RD1, right? So if we consider this as R pi, this is the, it is the R pi V pi by IB. If we consider this thing, so we will get R pi plus, that means it is series with 1 plus beta time RE1, right? RE1, 1 plus beta time RE1. So this is nothing but the input resistance, input resistance, input resistance. So simply we can see also that if RE1 in case of A1, this is one analogy, like if RE1 we makes it equal to 0, that means in case of A1 the RE1 is equal to 0, so then this Rin becomes R1 parallel R2 whole with parallel with R pi, right? So this thing is parallel with R pi. So this thing R2 parallel R1 parallel R2 parallel R pi, right? Okay. So what is the effect of this RE1? Is the input resistance is increasing or decreasing? How we can find out? So basically, so we can write 1 divided by R in, because it is a parallel combination, 1 divided by R1, right? All things are in parallel, so I am writing it as separate, plus 1 divided by R2 plus 1 divided by R pi plus 1 plus beta into RE1, right? So this is the thing. Now see one thing, if RE1, if RE1 is reduced, that means it is equal to 0, right? So what is happening, if this is reduced, the this entire thing will increase, that means 1 by Rin will increase, 1 by Rin will increase. So if RE1 is reduced, then 1 by Rin will increase, and that refers to R input is decreasing, right? R input is decreasing. So we can say for A1 Rin is less than A2, right? Less than A2. So in other way you can see, we can say like for A2 Rin is more than Rin of A1, right? So in case of A2 the input resistance is increasing. So in the given option, in A2 input resistance increasing, so A2 has larger input resistance, so it is satisfying. Okay, so this option is satisfying, but we want to see the other options also, whether it is satisfying or not. So A1 has a smaller voltage gain. Okay, so I will find out the voltage gain of this A2 model, that is A2, this small signal model. So what is so so okay, so what is the small signal gain of this amplifier? So basically this if we denote this as VO, that is the output voltage, so VO is nothing but this GM V pi is flowing from this side, GM V pi, so RC is parallel with RL, so here it will be minus GM V pi RC parallel with RL, right? So minus GM V pi RC parallel RL, because RC and RL are in parallel, so minus GM V pi into RC parallel RL, and we can we have already derived like IE is nothing but IB plus IC, which is IB plus beta times IB, which is nothing but 1 plus beta into IB, and this beta times IB is nothing but GM V pi, right? So this is GM V pi, so we can write IB as GM V pi divided by beta, right? Okay, so now what about this Vs, this voltage? So this Vs, here we are applying the Vs voltage, so Vs is nothing but this terminal is Vs, so Vs is nothing but this V pi, which is like this, plus this 1 plus beta time IB into RE1, right? So Vs is V pi plus 1 plus beta time IB, right? So V pi plus this IB we have already derived, this is GM V pi by beta, so 1 plus beta into GM V pi divided by beta, this is 1 plus beta IB into RE1, sorry, this will be into RE1, right, because it is voltage, so this much current is flowing, through RE1, right? So RE1, so this is RE1. So now if beta is very large, if beta is very large, so if beta is very large, that means beta is very greater than 1, so 1 plus beta is approximately equal to beta, and this beta cancels out, so we can say 1 plus beta by beta approximately is equal to 1, so that means this thing becomes 1. Okay, so if this thing becomes 1, that means this Vs is nothing but V pi plus GM V pi into RE1, right? Okay, now you can say V pi, if you take V pi common, this is RE1, or in other way V pi is nothing but Vs divided by 1 plus GM RE1. So you got this equation, V pi is equal to this, and so you have you have you have put the V pi with respect to Vs, right, in form of Vs, and also you know this V0 is nothing but minus GM V pi RC parallel RL, right? So V0 is minus GM V pi RC parallel RL, right? So you put the value of V pi here, right? So if you put, so minus GM Vs RC parallel RL divided by 1 plus GM RE1. This is okay, yeah, so this is okay, right? So now how can you get, so AV, that is the voltage gain, is nothing but V0 divided by Vs equal to minus GM RC parallel RL divided by 1 plus GM into RE1, right? So now, so this is the equation of the voltage gain of the common emitter amplifier with A2 configuration, right? So in the A2 configuration, we have the equation where RE1 is also the voltage gain is also dependent on RE1. But in case of A1, the RE1 is equal to 0 because it is directly the all the capacity all the resistances RE, the entire resistance is bypassed by the bypass capacitor, so RE is equal to 0. So if we put RE is equal to RE1 is equal to 0, so that means if RE1 equal to 0, then AV, that is V0 by Vs, is nothing but minus GM RC parallel RL, right? So this is the thing. So in case of this thing, so if we introduced RE1, then the gain is reduced, right? Gain is reduced. That means for A2, gain is reduced compared to A1. So in the given option, in A2 the gain is reduced, but here it is telling A1 has a smaller voltage gain, so it is wrong. So it will be A2 has the smaller voltage gain, right? So this option is not correct. Okay, okay, and okay, so in the option C it is telling like A2 has a larger DC bias current. So in case of DC analysis, we just ignore the capacitances, as I have already discussed. We just ignore the all of the capacitances. So this capacitance will not work, this capacitance not work, this capacitance will not work. So we will discuss entirely this thing for DC analysis. So from this circuit, and if we also for the A1 configuration, and if we also ignore these capacitances, so this thing is also we will consider during the DC analysis. So in the DC analysis, RE1 and RE2 is in series, and that will form the RE, that is the same thing. So for both the cases, for the A1 configuration and the A2 configuration, in both the cases the DC bias current IB will be same, right? Because these two circuits are absolutely same. That if these two circuits are exactly same, then IB is exactly same, and that means IC is equal to beta times IB, which is also exactly same. So A2 has larger DC bias current, that will be false. So the correct option will be A2 and A1 has the same DC bias current. Okay, okay. And in the first option, it is saying like A1 allows a larger input voltage amplitude without causing distortion in the output voltage. Okay, I will discuss this thing. Uh, I will discuss this thing. Okay. Okay, so now what is happening? So if we consider this small signal analysis, so in this small signal analysis, how this V pi and Vs is related? So so I so I am drawing this small signal model again. Sorry. So there will be Vs for A2 configuration, right? A2 configuration. So there will be Vs, there will be R1, there will be R2, all are connected to ground, and then there is R pi, across which V pi drop is there, and then here is RE1. So this is the emitter terminal, this is the base terminal, and here a current source which is GM V pi that will come, and here you have RC, and here another you have RL. Okay, and now this thing, so this thing is the collector terminal. So here it is collector current which is flowing through this IC is equal to beta times IB, right? And here you have the base current IB, and here you have this IE, which is beta IB plus IB, right? These two current is flowing through this, so that is beta plus 1 into IB. Okay, so now during small signal analysis, what is the value of V pi? So V pi is nothing but, so Vs is nothing but this is the, if this is the Vs, if this thing is Vs, I'm using this green pen. Okay, so this thing is Vs, so Vs equal to V pi plus beta plus 1 IV into RE1, and now this beta time IV is nothing but GMV pi. That means IV is GMV pi divided by beta. So Vs is V pi plus beta plus 1 IV is GMV pi divided by beta into RE1. That means Vs divided by V pi. Vs is nothing but V pi 1 plus beta plus 1 beta into GM RE1. And so if you consider this thing, V pi by Vs is 1 divided by 1 plus beta plus 1 beta into Gm into RE1, right? So this thing, so this is nothing but, we can say, R pi I beta divided by R pi into I beta, right? Because this is the V pi plus Re into beta plus 1 times into IV. So that means R pi divided by R pi plus 1 plus beta into RE1. Now due to according to the small signal analysis, this V pi should be very less than Vt. Now here you can see V pi is nothing but Vs into R pi divided by R pi plus 1 plus beta into RE1. That should be very less than Vt, or you can say this Vs small signal analysis is RT Vt time R pi plus 1 plus beta into RE1 divided by R pi. Okay, so you can see this thing, entire thing is much more greater than 1. This thing is much more greater than 1, very larger than 1. So Vs should be very less than k times Vt, that means very large amount. So we can say that for the A2 configuration, so if this Vt is 26 volt, that means in case of A1 configuration you can apply 10 times smaller 2.6 millivolt maximum this amount of AC voltage in case of A1 configuration, because in case of A1 Vs should be very less than Vt, right? In case of A2 Vs should be very less than k times Vt. Suppose k is equal to 10, so that means this is 260 millivolt. So that means you can easily apply 26 millivolt amount of input voltage without distortion. It can be amplified, right? So in case of A2, so in the given option it is telling like A1 allows a larger input voltage amplitude without causing distortion in the output voltage. So instead of A1 it will be the A2 will be the right answer. So this option is wrong. So among these four options, A2 has a larger input resistance. This is the most suitable answer for this. The others answers are wrong, because in the first option it will be the A2 allows a larger input voltage amplitude without causing the distortion in the output voltage, and A2 has a larger DC bias current. That will be not the right answer. A1 and A2 both have the same amount of DC bias current. That will be the right answer. And A1 has smaller voltage gain, so that will be the A2 has a smaller voltage gain, as we have already discussed. So this is the entire analysis of this. So see, one thing that you have not to remember each of the things, but instead of that, what you can do, you can just go through the analysis, how the small signal analysis is formed, and you just apply a KCL and KVL, and you can easily see that how it can be. You can also interpret the result in a different manner. uh, while you draw this circuit, you can see, like, for the input resistance in this circuit, it is R1 parallel R2 parallel R pi. So which will be the smaller, that will be the answer. But here R1 parallel R2 parallel R pi plus some extra amount, right? So that means this A2 has this extra amount. If it is getting, then it has a larger input resistance, because this r pi with series with something that will be increased, and that means that the entire input resistance with the parallel combination of those, that means that thing is also increased. So you can interpret easily by analyzing this thing. But at first it is preferable to go through the analysis, uh, uh, go through by circuit analysis, KCL and KVL, then you can easily understand. In the other way, you can also say, for the voltage gain, here whatever Vs are you applying, it is coming in this V pi, and it is simply GM V pi is multiplied with RC parallel RL. But here what is happening, so whatever V pi is so whatever Vs is there we are applying, that is the combination of V pi plus the voltage drop across RE. So V pi is basically less than this Vs, right? Because some amount of this voltage drop is contributing by this Vs, right? So V pi is small, so that means the GM V pi is small, because here entire Vs is applied through V pi. But here what is happening, the part of Vs is appearing as V pi, and then it is getting multiplied with GM, and then it is flowing through RC parallel R. Okay, so by this way also you can interpret the result, or you can easily analyze the result easily, and you can get the desired answer. Okay. Okay, so this is the entire analysis of question 1. So I hope that it is clear very much. So okay, so now I will go to the question number 2. So in the question number 2, now it is the basic questions of op-amp. So this is op-amp is basically operational amplifier. Operational amplifier. Amplifier. So in the circuit shown in the figure, the op-amp operates in the open loop configuration. Open loop means there is no feedback. So in the control system, you have already studied, like if you have gone through the control system, then you can say that if a system has some feedback path, some feedback is there, this feedback path is, then the system is called the closed loop system. Closed loop system. But if there is no output to input path, or any feedback path, feedback means output to input path, then that is called the open loop system. Open loop system or open loop configuration. So here you are applying some input and you are getting the output. But if you are not feeding any partial amount or the full amount of output to the input, so that means there is no feedback path. So if the feedback path is not there, so that means this is in open loop configuration. So in an op amp, suppose there are two voltages applying, and you have this VO. So this VO output will be open loop gain of the amplifier. Suppose AOL refers to the open loop gain of the amplifier, V plus minus V minus. That is, it is just amplify the difference of the input signal. That is whatever the difference, what is the difference that is applying, we are applying in the input terminal, that is V plus minus V minus. V plus is this terminal, this is the plus terminal, right? So here in the plus terminal whatever voltage you are applying, that is referred to as V plus, and in the minus terminal whatever voltage you are applying, that is referred to as a V minus terminal. So V plus minus of V minus, that multiplied with AOL, that is the open loop configuration, that the gain of open loop configuration. So if it gets multiplied, then you will get VO, right? Okay, so this is the thing. And so basically here in the question it is asking, in the circuit shown in the figure, the op amp operates in the open loop configuration. What is the duty cycle? So you must know about the duty cycle. So what is the duty cycle I am discussing? So for any signal there is a duty cycle. Duty cycle means, suppose you have one square wave. This is some periodic signal. Okay, suppose this is xt, that depends on time t. Okay, so it has some value, suppose a, and this is minus a, or it has some value, square signal. So this is 0 and this is the t, that is the time period of the signal t. So after t it repeats, right? Okay, to t. Suppose till this point it is known as, this thing is known as t on, that means within this interval the output is high, and with this interval the output is low, t off. Okay, so the duty cycle is referred as, duty cycle is t on divided by t on plus t off, that means t on divided by entire time period t. So duty cycle we generally refer to as percentage. So if we multiply percent 100, then we get the percentage sign, right? So duty cycle percentage is t on by t into 100, that much percentage is the duty cycle. Okay, you understood, right? Okay, now in this circuit it is telling like, the op amp operates in the open loop configuration. What is the duty cycle d? Defined as a fraction of time, defined as a fraction of the time VO is high. So while the VO is high, what is the duty cycle, right? So now I am redrawing the circuit, plus minus. So this is R2, this is R1, this is 2k, this is 1k, this is 3 volt, and here you have 4 sine omega t minus 1, that much volt. Okay, okay, and this thing is VO, right? So now what is the voltage that is applying through this? So in the open loop configuration you must remember that the input current to the op amp is equal to 0, because it has very high amount of resistances. So for the open loop configuration you must remember one thing. First thing is AOL is nearly tends to infinity for the ideal op amp configuration, the open loop. Second thing, Rin is always very high. That means the current drawn in the op amp is ideally equal to 0. And the third thing is Rout is equal to 0. Means whatever amplified, what is the amplified version of the input signal that entirely appears across the load. That means that Rout is equal to 0. Okay. So you must remember these three things. So now here also the input, there should not be flow of current, so I is equal to 0, so the entire current will flow through this thing. So this is basically, you can see it is a voltage divider circuit. So V minus will be nothing but 3 into 2k divided by 2 plus 1, which is 3. So 3 cancels out, so it will be 2 volt. Okay, 2 volt. So V minus is 2 volt, and V plus is this 4 sine of omega t minus 1. So what will be the VO? So as I have already discussed, VO will be nothing but AOL times V plus minus of V minus. Okay, so this is AOL times V plus is 4 sine omega t minus 1 minus 2, right? Minus V minus is 2, so minus 2. So this is AOL 4 sine omega t minus 3. Okay, now you have to draw the waveform, that how it looks. So if you draw it, so if you draw it, so if you draw 4 sine omega t, suppose it is 4 sine omega t versus omega t. If you draw this thing, so it will be simply this, right? So it has a certain period, that is 0, this is 2 pi, this is pi, and this is pi by 2, and this is 3 pi by 2, right? After 2 pi, then again it repeats, right? So it will be like 4 pi and like that. Okay, okay. So here in this signal, if it is asked like what is the duty cycle, so half of the time period it is on, right? So duty cycle D is equal to T on divided by T into 100. So T on is what? It is pi amount of time. So pi divided by the entire time period, which is 2 pi, into 100, that much percent, right? So pi cancels out, so that will be 50%. If in the question it is 4 sine omega t, so if it is question, it is asked like what is the duty cycle of 4 sine omega t, then that will be 50%. But here now it will be 4 sine omega t minus 3, that is amplified with some amount, so that will not vary the duty cycle because it is amplified. Because whether the peak is like 4, or if it is amplified by 2 amounts, the peak is 8, the duty cycle remains the same, right? If it is also amplified this thing, but the duty cycle remains same, right? Okay, so this AOL will neglect this thing, and we will see that how this waveform looks like, and then we will find the duty cycle of this. So 4 sine omega t minus 3, that means it can maximum the sine omega t maximum go from minus 1 to 1. So sine omega t, it can goes from minus 1 to 1. So 4 sine omega t, it can goes from minus 4 to 4. And if you consider 4 sine omega t minus 3, so it can goes from minus 7 to minus 1, right? Minus 3 if you do in both the sides, so minus 7 to minus 1. So that means if this is the x-axis, omega t axis, and this is the VO, so this axis, then with respect to minus 3, it oscillates, right? So it will go to 1, so it will be like this thing, right? So it will vary from minus 7 to 1. So you need to find out this entire period, throughout this time the the signal is on. So you should find out this zero crossing part, that is here. In here you have V0 is equal to 0, and here also you have this. So V0 is equal to 0 means 4 sine omega t minus 3 is equal to 0. That means 4 sine omega t equal to 3. So sine omega t is equal to 3 by 4, that is 0.75. So omega t will be nothing but sine inverse 0.75. So I am calculating this thing, 0.75 sine inverse 48.59. So it will be 48.59 degree. So that will be the thing, right? Okay. So now, so that means here omega t value is 48.59 degree, and we know the peak here. In the peak the value is pi by 4, sorry, pi by 2, right? Because here it is pi by 2. In the peak here it is pi by 2, so here we have pi by 2, that means 90 degree. So for 90 degree minus 48.59 degree, that means in this period this is on. So this thing is nothing but 90 minus 48.59, which is equal to 90 minus 48.59, 41.41. So 41.41 amount, and as it is symmetric, so here also it will be 41.41. So it will be the entire time t will be 41.41 into 2, that much degree, that means 82.82 degree. So during this much time, this much omega t, sorry, omega t, for this much omega t, the signal is on, that means the signal is high, that is greater than 0, right? So the duty cycle d will be 82.82 degree divided by the whole time period, which is nothing but 2 pi, right? 0 to 2 pi, 0 to 2 pi, 0 to 2 pi, 0 to 2 pi. So that is 360 degree. So 360 into 100, that much percent. So it will be 82.82 divided by 360, so that is 23%, or in short we can write 0.23. So the correct answer will be here option C. So it is 0.23, that is the 23%. In the 23% amount of duty cycle during this condition, the fraction during this fraction of time VO is high, that means VO is greater than 0. Okay, yeah. So this is the thing, that how we can calculate this thing, during what time this thing is on. Okay, okay, okay. So now the next question, in the op-amp circuit shown in the figure, what is the value of VO? So VO. So see, here is it is a closed loop configuration. Closed loop configuration. Why this is a closed loop configuration? So this is a closed loop configuration because there is some path from output to input. This resistance is connected, right? So there is some feedback path. Feedback path. That means path from output to input. So this is some closed loop configuration. So in the op-amp circuit shown in the figure, what is the value of VO? It is asked what is the value of VO. So now how we will do this? So here it is a negative feedback. So here it has a positive. Uh, so it's a negative feedback. Why it is a negative feedback configuration? Negative feedback. Why? Because the output to input connection is in the inverting terminal. So minus this terminal is known as inverting terminal, and this plus sign, this thing is known as non-inverting terminal. So this is the inverting terminal, and this thing is known as non-inverting terminal. So that means in the the feedback path connects output. The feedback path is connected from output to the inverting terminal. So that means it is a negative feedback configuration. So during negative feedback configuration, so so the virtual ground concept is held in the negative feedback configuration. Now we have to find out what is the value of V plus virtual. Ground means V plus minus V minus is equal to 0, right? You understood, right? How it is getting. Suppose this output VO is nothing but AOL into VID, that is the difference. So AOL into V plus, sorry, V plus minus of V minus. So now this AOL is very high and VO is also limited. So V plus minus V minus is nothing but VO divided by AOL, and AOL is very high and VO is some limited, it is limited. So that means V plus minus V minus almost tends to 0. That means V plus is equal to V minus, almost equal to V minus. So that means it is a virtually short concept, virtually short. That means both are virtually short. Now if we put one terminal as ground, other terminal will be also grounded, so it is virtually grounded. Understood, right? Okay, so this is the virtual ground concept. That means V plus is equal to V minus. So now we need to find out what is the value of V plus. So V plus is nothing but, as it is an op amp, the current will not flow through from this side. So what is the voltage across this? That will be the simply the voltage divider rule. If we apply the voltage divider rule, we get 0.6 volt into 1k, that means 1 divided by 1 plus 2k, 1k plus 2k, right? So 0.6 divided by 3, so it is 0.2 volt. So V plus is 0.2. So V minus will automatically equal to V plus because its virtually ground concept is hold. So that will be also 0.2 volt. So this terminal, so this terminal also is 0.2 volt. So this terminal is 0.2 volt and this terminal is also 0.2 volt. So no current I1 is equal to 0. No current will flow through this terminal, right? Because both in the both side the potential are same. So no current will flow in the terminal. So the only current will flow through this, right? I2 current through this 2k, right? So current through 2k is, it is 0.2 volt minus, here is 0.5 volt is applied, so minus 0.5 volt, this thing divided by 2k, so that much milliampere. So it is zero point 0.2 plus 0.5, right? So 0.7 divided by 2 milliampere. So this is the I2 current that is flow. And now as there should not be any current flow in this side, so this entire I2 current will come from this side I2. So here it will be positive sign, here it will be negative sign. So what will be the value of V naught? So V naught will nothing but V minus the voltage across V plus this same amount of I2 will flow in this side because there is no current in this side, and there should not be any current flow through this side. So this entire amount of current will flow through this side. So I2 into 2k, right? Now V minus we have already found out, that is 0.2 volt plus I2 is nothing but 0.7 divided by 2, 0.7 divided by 2 into 2, that much milliampere. So 2 cancels out, so it will be 0.2 plus 0.7 milliampere, sorry 0.7 volt, because this is milliampere and this is the, and 2k is the resistance, so it will be volt, so it will be 0.9 volt. So the correct answer will be option A, that is 0.9 volt. Okay, so it is very simple thing. You have to just do the KCL KVL accurately and you can easily get the answer. Whatever is the answer, you can easily get. Okay, so I hope all the things are clear. So yeah, so I want to discuss one thing, right? Like in the, so what happens is, this is the internal configuration of op amp. Internal configuration, internal configuration, internal configuration of op amp is like this. So this is the input resistance Ri. So whatever the Vi that is created over here, and here is Ro. It is connected to this one. Now what happens is, in case of ideal op amp, this input resistance Ri would be very high. That means that tends to infinity. So this practically the range is in mega ohm. So it is very high. So we can consider it as open circuit. In the open circuit, there you have Vi. Similarly, you have some gain, that is AVVI, and this AV is very high. Ideally, it tends to infinity. Practically, it can be like 10 to the power 3 times 3 order. Like it can convert millivolt to volt like that. And this Vi and this R naught is basically is equal to 0. So that means R naught RO output resistance equal to almost equal to 0. Practically it's in ohm range, so we ignore this thing. And so whatever the voltage that is amplified, so the entire amount of voltage appeared in the load term, okay, in the output term. So this is the basically internal configuration of an op amp. Okay, okay, so I am moving to the next question. What is the gain VO by Vi of the circuit shown in the figure? So what is the gain VO by Vi of the circuit? Yeah, so basically so here it has two op amp that is cascaded. Cascaded means the output of an op amp, this is op amp 1, the output of op amp 1 is fed to the input of op amp 2. So that means, so suppose you have some amplifier 1, and if you have some amplifier 2, suppose you are giving an input Vi and output is Vo. Suppose this amplifier 1 have gain G1 and this amplifier have gain G2, then Vo is nothing but G1 into G2 into Vi, right? Because if input Vi is applied and G1 is the gain, then G1 Vi is applied over here and G1 Vi is multiplied with G2 and it will convert to Vi. So Vo divided by Vi, which is the voltage gain of the amplifier, cascaded amplifier, which is G1 G2. So similar thing is there. So out, let's suppose the output of op amp 1 is denoted as Vo1 and the output of op amp 2 is denoted by Vo2. So Vo2 is nothing but Vo, right? So what is the value of Vo1? So see, so this is the inverting, this is the, at first you need to see what is the feedback. So this is the negative feedback, negative feedback, negative feedback. Why? Because in the negative terminal, because the there is some feedback path from output to the inverting terminal, right? Okay, so negative feedback, so negative feedback, and the input is applied in the positive terminal, non-inverting terminal, right? So this is the non-inverting and this is the inverting, this is the inverting. So this is applied in the non-inverting terminal, so that means it is a non-inverting amplifier, right? So in case of non-inverting amplifier, what will be the Vo1 output of the amplifier 1? That is, what is the input voltage 1 plus R2 divided by R1, right? R2 is 10 and R1 is 2.7, right? So it will be Vi 1 plus 10 divided by 2.7, right? Okay, so this is the VO1. This is the first thing. So this V1 is applied over here also, and here also it's a negative feedback in the second op amp. This is for the first op amp. This is first op amp, analysis we have done, and now we have second op amp. So in case of second op amp, here also the feedback path is in between output to the inverting terminal of the op amp. That means it is a negative feedback. So it is a negative feedback. So it is a negative feedback, and the input signal, that is VO1 is applied in the in the inverting terminal. That means it is a inverting. So this was non-inverting amplifier, and now it is the inverting amplifier. Inverting amplifier. So in the inverting amplifier, the output voltage VO2, which is nothing but VO, the same as VO, is minus R2 by R1 into VO1, where R2 is this feedback resistances and R1 is this input resistances, right? So it will be minus 8.2 divided by 1.2 VO. This is the VO. Now if we put this VO1 over here, then what we get? Minus 8.2 divided by 1.2, 1 plus 10 divided by 2.7, right? Okay. So now what is the answer? If we do 10 divided by 2.7, so 3.70. So it is minus 8.2 divided by 1.2 into 1 plus 3.7. That is minus 8.2 divided by 1.2 into 4.7. So 8.2 divided by 1.2. So this is minus 32.11, minus 32.116. So this is the overall gain. So here the correct option will be option B, that is minus 30. Okay. So you all understood that how we have done. So there is basically two op amp which is cascaded. That means the gain will be multiplied. If the first op amp has gain G1 and the second op amp has gain G2, then G1 into G2 is the overall gain. So now what we have done in the first, we have seen that in the for the first op amp, how it is connected, is it is in negative feedback or positive feedback? It is in negative feedback. And why negative feedback? Because there is a path between the output terminal and the inverting terminal, right? So there is a negative feedback, and and this first amplifier is a non-inverting amplifier because we are applying the voltage in the non-inverting terminal. So in the non-inverting negative feedback amplifier, the gain is written as VO equal to Vi into 1 plus R2 by R1. So R2 is what R2 is the feedback resistance, or R1 is the input, the other resistance, 10 by 2.7, right? And in the second op amp, and this output is fed to the negative terminal of the op amp. And then the second op amp is also the negative feedback. That means the output, the feedback path is connected between the output and the inverting terminal, and also here the input voltage is applied in the inverting terminal. So that means it is an inverting amplifier, right? And the for the inverting amplifier, the gain is nothing but minus R2 divided by R1. So minus 8.2 divided by 1.2, and that will be multiplied with 1 plus 10 divided by 2.7. So minus 32.116 comes. So minus 32 is the correct answer. Okay. Yeah. Okay. Moving forward to the next question. Assuming that the op amp in the figure is operating in the linear region, what is VO? Okay, so I have already told you that you must see at first the which feedback is there in the amplifier, right? So here there is a path between the output terminal and the inverting terminal, and as well there is also another path from output terminal to the non-inverting terminal, right? Inverting terminals and non-inverting terminals. So we are not sure that whether this op amp is in negative feedback or in positive feedback. So whether it is in negative feedback or it is in positive feedback, uh, uh, so to determine this we have some method, right? How we can see that it is in positive feedback or in negative feedback? So you first, the step one to see whether, so so if there is both the feedback path to the op amp to see whether the op amp is in negative feedback condition or not, we have to follow the respective steps. Okay, so how we can find out? So step 1, ignore the op amp or remove the op amp. Ignore the op amp, that means remove the op amp. Okay, step 2, nullifying the DC sources. That means if we are applying this there Vi, so Vi we connected to ground, or if there is any current source then that will be open circuit, right? That, so nullifying the DC sources, all the sources we are nullifying the sources, input sources we are nullifying this. Okay, and then step 3, put a test voltage V test, suppose, at VO, and calculate V minus and V plus separately. Okay, so you should find out what is the value of V plus and V minus. Okay, so now we are just ignoring the op amp. So here we have 4.7k and you are nullifying the input, so it is connected to ground, and then you have 12k, and then you have VO, right? And here also you have 91k, and then you have 8.2k. Okay, okay, so these are the things. Okay, now what you have to do, you have to apply a test voltage over here. So V test. See, if we apply the V test over here, let us consider this is V minus and this is V plus. So V minus will be V test into, this is simply voltage divider rule, 4.7 divided by 12 plus 4.7. which is 16.7 equal to, so 4.7 divided by 16.7, which is 0.28 V test, and V plus is equal to V test multiply with V test into, here also it's a simple voltage divider rule, 8.2k is going to ground plus 99.2, right? So it will be 8.2 divided 99.2, that is 0.082 V test. So now if step number 4 is that, step number 4 is that calculate V, that is the difference, right? So V, calculate V minus minus V plus, okay, and if V minus is, so here if we calculate V minus minus V plus is nothing but 0.28 minus 0.082 into V test. So 0.28 minus 0.082, so that is 0.198 V test. And if we consider it as alpha V test, so here alpha is greater than 0. Then if alpha is greater than 0 and also this V minus terminal is negative and V plus terminal is positive, then it is a negative feedback. So if alpha is greater than 0, so V minus is connected with the negative part, yeah. So you can see that V minus is connected to the negative terminal of the op amp, and here for the V plus, this is the V plus, this terminal is connected to the positive terminal of the this part. So that means that there is a negative feedback. Because why? Because you have calculated that the V minus is something greater than the V plus, so V minus is greater than V plus, so that means this terminal should be connected to the negative part of the op amp, and if it is connected to the negative part, V minus part is connected to the negative part of the op amp, that means this whole amplifier is in the negative feedback. So you have understood that the that the entire amplifier is connected in the negative terminal, right? So it is a negative feedback. Okay, so now you have to proceed with the question that what is the uh, amount of VO is what? Okay, so how you calculate the amount of VO? So suppose here the potential is Vx, so that means whatever current is flowing through this in this side, this is 0.4 minus Vx divided by 4.7, that is equal to, because no current can flow through this to this op amp, equal to Vx minus Vo divided by 12, right? So it will be 4.8 minus 12 Vx equal to 4.7 Vx minus 4.7 Vo, right? So 4.7 and 12 Vx means 16.7 Vx is equal to 4.8 plus 4.7 Vo, right? So Vx will be 4.8 divided by 16.7, so it will be 0.287, 0.287, 0.281, so it is 0.28 Vo. Okay, this is one thing, right? And if we put another KCL over this point, then we can get Vo that is 0 minus Vx, 0 minus Vx divided by 8.2k, whatever the current is flowing through this terminal, is equal to Vx minus V0, because no current is flowing through this terminal. So Vx minus V0 divided by 91k. So it is VO divided by 91 equal to Vx divided by 1 divided by 91 plus 1 divided by 8.2. Okay, so 1 divided by 91 plus 1 divided by 8.2, 0.133. So it will be 0.133 Vx. So V0 is equal to, multiplied with 91, that is 12. So it is 12 Vx, and 12 Vx, and we know the value of the Vx. So if we put the value of Vx over here, we can get VO is 12 times 0.287 plus 0.28 VO, right? So it will be 12 into 0.287, which is 3.444 plus 12 into 0.28, 3.36 VO. So if we move VO in other side, that is 2.36 VO is equal to minus 3.444. So that means this VO will be minus 3.444 divided by 2.36. So 3.444 divided by 2.36. So that comes out minus 1.459. So this much volt is there. So minus 1.44 will be the correct answer, right? If we approximate this, so minus 1.44 will be the correct answer. Okay. So in this way, we can go through the problem. At first, we need to determine whether it is negative feedback or not, because in the positive feedback, the entire analysis will be different. In the negative feedback, it is a stable circuit. In the positive feedback, it is an oscillating circuit. So at first we need to determine whether it is in negative feedback or not, and if there is a feedback path between the output to the inverting terminal and output to the non-inverting terminal both, then we need to follow these following steps to find out that whether it is in negative feedback or not. If it is negative feedback, then we can apply the concept of virtual ground. Otherwise, the virtual ground concept will not be there, virtual short concept will not be there. So then we consider the virtual ground concept, and then only we process with the V plus equal to V minus, and then we'll go through the KCL or KVL analysis, and simply we can get the answer. Okay, yeah. So this is the thing. So to analyze this, we first, what is the step? I am just repeating once again. So we have to ignore the op amp. That means we must remove the op amp, and then we must nullify the DC sources. Then we put a test voltage and at VO, and calculate the V plus and V minus separately, and then we calculate V plus minus V minus, whether it is greater than 0 or not. If it is greater than 0, and then V minus is connected to the negative terminal, that means the negative feedback, and V plus terminal is connected to the positive positive terminal, and that is the negative feedback. So the entire op amp is in the negative feedback, and then we just apply the KCL and KVL, and we can easily found out the entire thing. Then only this terminal is Vx, and this terminal also we consider Vx. But if it is not in the negative feedback condition, then we cannot apply this concept, that is the virtual short concept, over this V minus and V plus of the op amp. Okay. Okay, the next question: what is the VO by Vi in the circuit shown in figure? So this is also simple. So what is the current whatever the current flowing through this, that much current should be flowing through this. So let us consider this terminal as Vx. So Vi minus, so this is ground, so this terminal also is equal to ground because it's a negative feedback terminal. So virtual short concept holds, virtual ground concept holds. So Vi minus 0 divided by 1.2 So at first we have seen that this is a negative terminal, right? Because the feedback path is between the output and the inverting terminal. And then we proceed with the virtual short concept. So virtual short means whatever the V plus is there, that should be in the V minus. And this plus terminal is already connected to the real ground. So this minus terminal will also be close to the ground. That means close to the 0 volt, but not actually ground, but we can consider it as ground. So this is known as the virtual ground. So now this is 0 volt. So basically the current flowing through this Vi minus 0 is divided by 1 by 2, and the entire current will flow through this terminal, because in the op amp there should not be flow of current. So is equal to Vi minus Vx divided by 9.1. So Vi divided by 1 by 2 equal to Vi divided by 9 by 1 minus Vx divided by 9 by 1, right? 9.1. So now, sorry, so this will be 0 minus Vx, right? Yeah. So Vi minus 0, 0 minus Vx. So here it will be minus Vx 9 by 1. So Vx is nothing but minus 9.1 divided by 1.2 into Vi, right? Yes. Now what is happening? So now from this there we need to apply another KCL. So minus Vx divided by 9.1, that means whatever current is applying through this terminal is equal to nothing but Vx minus Vo divided by 8.2, that means the current flowing through this and the rest of the current, plus Vx minus 0, that means Vx divided by 4.7, right? So here it will be Vo divided by 8.2 is equal to Vx divided by 1 plus 8.2 plus 1 by 4.7 plus 1 divided by 9.1. Okay, so 1 divided by 8.2 plus 1 divided by 4.7 plus 1 divided by 9.1. So it will be, so 0.444 Vx multiplied with 8.2, that is 3.64. So Vo is nothing but 3.64 Vx. And now if we put the Vx over here, then Vo is equal to 3.64 into minus 9.1 into 1 by 2 by Vi, or Vo divided by Vi is equal to minus 3.64 into 9.1 divided by 1.2. So 3.64 into 9.1 divided by 1.2, which is nothing but minus 27.6. So this is the Vo by Vi, which is nothing but minus 27.6. Okay, so this was very easy. In the next problem, in the op-amp circuit shown here, what is the value of I1? So to find out the value of I1, we need to find out the voltage over here. Okay, so suppose we consider this voltage. So there, so okay, so you have to find out again the two thing, because there is a positive also and negative also. So you have to find out that what is the voltage over there, and uh, so is it in negative feedback or not. So I am assuming it is a negative feedback. So now how we can proceed? So so suppose this terminal is Vx, so this terminal will also be Vx. So Vx, how it can be? So the current flowing minus 1 minus Vx divided by 1.8, that means in this direction, that will be equal to Vx minus Vo divided by 1.8. 1.8 1.8 cancels out, so that means twice Vx plus 1 equal to Vo, right? Okay, So VO is twice Vx plus 1. Okay, Vx is twice Vx plus 1. Okay, okay, and here also, here it is Vx. So in the from the Vx there is two terminal, it is 4k and 2.2k, both are going to ground. So 4k and 2.2k is in parallel. So 4k parallel 2.2k, how much it's coming? 4 into 2.2 divided by 6.2. So 4 into 2.2 divided by 6.2, it is 1.42. Okay, 1 to 1.42 kilo. So now how it is happening, like here it is the VO. So VO minus Vx divided by 2.2 is equal to Vx divided by 1.42, or VO divided by 2.2 equal to Vx 1 by 4.2 plus 1 by 2.2. So VO will be nothing but Vx into 2.2 divided by 2.2 into 1 divided by 4.2, 1 divided by 2.2, right? So how much it is coming? 1 divided by 4.2 plus 1 divided by 2.2 into 2.2. So it will be 1 divided by, so 1 divided by 4.2 plus 1 divided by 2.2. Sorry. Okay. So it will be 1.42. Sorry. This will be 1.42. So this will be 1.42. So 1 divided by 1.42 plus 1 divided by 2.2 into 2.2. Yeah. So it comes out to be 2.55. So 2.55 Vx. So V0. So here it is equation 1 and here it is equation 2. So if we compare equation 1 and equation 2, 2Vx plus 1 is equal to 2.55 Vx. That means 0.55 Vx is equal to 1. That means Vx equal to 1 divided by 0.55, which is 1.818. So that much volt is there. Now what is I1? I1 is basically this Vx divided by 1.42 kilo ohm. That is 1.811 divided by 1.42. That much milliampere, and that comes out to be, sorry, the I1 current is flowing through this 4k, right? So through this 4k means here instead of 1.42 kilo ohm you should write 4, because I1 current is flowing through this and rest of the current will flowing through this thing, through this 2.2k, right? So 1.818 divided by 4 is nothing but 1.818 divided by 4, which is 0.4545 milliampere. So the correct answer will be 0.45 milliampere, right? Okay. Okay. The next question, for the Sagi shown in the figure, VO is given by VO equal to K1 V1 plus K2 V2. So what is the value of K1? So it is also a negative feedback. So if V2 is applied over here, so this entire terminal, the potential is V2. So here V1, if we apply the KCL, V1 minus V2 divided by 5K is equal to V2 divided by 15, V2 divided by this thing, and plus V2 minus V0 divided by 10. So V1 minus V2 equal to V2 divided by 3 plus V2 minus V0 divided by 2. So if you multiply 6 in the both sides, 6V1 minus 6V2 is equal to 2V2 plus 3V2 minus 3 VO. So now this 3 VO is equal to 2V2 plus 3V2 plus 6V2 minus 6V1. So that means 3VO is equal to 2 plus 3 5 plus 6 11. So 11V2 minus 6V1. So now V0 is equal to 11 by 3V2 minus 6 by 3V1 means 2V1. So VO is nothing but minus 2V1 plus 11 by 3V2. So if VO is written as K1V1 plus K2V2, so V1 is written but K1V1 plus K2V2, so the K1 will be minus 2, right? So the correct answer will be minus 2. This was very simple question. Okay, yeah. So the next question, in the same circuit, what is the value of K2? So we have already found out the K2 is nothing but 11 by 3. So K2 is nothing but 11 by 3. So what is 11 by 3? 11 by 3. 3.67. So 3.67. Same problems. Yeah. So it will be 3.67. The same thing, right? Okay. Okay. The next question. Next question. It is asked, for the circuit shown in the figure, what is the value of VO? So here it is also a negative feedback problem. So here whatever the V minus, that will be is equal to V plus. So V plus is 2 volt. So that means V minus is also equal to 2 volt. So here it is 2 volt. This 2 terminal is in 2 volts. So no current will flow through this path. So this resistance is not of any use. So 2 volt is over here also. So the current flowing through this terminal is 2 volt minus 1 volt divided by 1.5 milliampere. So this much current will flow, that means 1 divided by 1.5 milliampere. So now so this much current is flowing through this terminal. If it refers to I1 is over here, and no current will flow from this side and no current will flow in this side. So this I1 entire current flow through this side. So whatever the voltage drop over here, so VO will be nothing but the voltage over here, that is V minus plus of I1 into 0.82, because I1 is in milliampere. So it should be represented in kilo ohm, then only the volt will come. So V minus is nothing but 2 volt plus 1 by 1.5 milliampere, that is I1, into 0.82, right? So 0.82 divided by 1.5, that is 2 plus 0.5467, that means 2.5467. So that is 2.55, closely equal to 2.5. So the correct answer will be option A. Okay. 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 So the next question. In the circuit shown in the figure, the op amp operates in the open loop configuration. That means there is no feedback path. What is the duty cycle D, that is defined as the fraction of time when VO is high if the wiper is in top position? So this is basically a potentiometer problem. So if this potentiometer is in the top position, that means this potentiometer is connected through this. That means this terminal is shorted with this terminal. That means this is directly connected to ground. So there is no use of this 2.2k resistor. So I am drawing the circuit again. So now the equivalent circuit will be, and here the input is plus 12 volt minus 12 volt. Okay. So now here this terminal is directly connected to ground, minus terminal. So V minus is equal to 0, right? Because it is connected to ground, V minus. So now what is happening, right? the output of this is will be, as I have already discussed for the open loop configuration, this is V plus minus V minus AOL into V plus is this 12 volt, right, sinusoidal signal, so V plus minus 0, that means AOL into V plus. So whatever the input, that the voltage that is applying in the input terminal, that will be multiplied with some amount, that is the gain, open loop gain, and that will appear in the output terminal, right? So the output VO will be, if the input is this, the output will be K time multiplied with V plus, right? K is AOV, right? AOL, open loop gain. K is AOL, right? Okay. So now, what is the duty cycle of this? For the input signal, this 12 volt to 12 volt triangular signal, the duty cycle, so duty cycle is T on divided by T into 100%, right? So T on is half, right? 0 if it is 0, if it is T by 2, if it is T, so you can write as T by 2 by T into 100%, so TT cancels out, so it will be 50%. So similarly in the output also, the same signal is just get amplified, but the duty cycle remains the same, it is also the half of this thing, right? So it will be same, T by 2 divided by T into 100%, that means T and T cancels out, so it will be 50%. Okay, so the correct answer will be option B, 50%. Okay, the next question, what will happen if the wiper is in the middle position? So it is a potentiometer, so if it is in the middle position, then the equivalent circuit diagram will be one point one K, because after 1.1 K it is connected to the ground, so 1.1 K will appear over here, and it is 3.3 K, and it is 10 volt, and it is plus 12 volt, it is minus 12 volt. So whatever the voltage that will apply in the negative terminal, that will be 10 into 1.1 divided by 1.1 plus 3.3, right? Voltage divider rule. In the earlier it was directly connected to ground, so V minus was 0 in the previous case, but here it will be the voltage division of this two resistor, right? Voltage divider rule if we apply, so 10 into 1.1 divided by 3.3, so 10 into 1.1 divided by 4.4, so 1, this is 4, this cancels out, and this is 2.5 volt. So whatever will be the VO, it will be nothing but AOL V plus minus V minus, right? So AOL V plus is this triangular wave minus 2.5 volt, so V plus minus 2.5. So we have seen earlier also that AOL will not affect the duty cycle of the signal, so we ignore this thing and we will try to draw V plus minus 2.5 volt. Say, so if we draw V plus minus 2.5 volt, earlier it was minus 12 to plus 12, so now it will be minus 12 to plus 12 was the V plus. Now V plus minus 2.5 volt, that will be minus 14.5 to 9.5. Okay, so that will be, so like this. So here this will be 9.5 and this will be minus 14.5, and earlier it was, so like this. Okay, so that means it is now shifted. Okay, so earlier it was like this. Okay, so what is the thing? So okay, so so now, sorry, so okay, I am drawing this thing again. This is the input, that is 12 volt, it is minus 12 volt, and now it is shifted. Suppose this is here, now it is shifted over here. Okay, so it will be shifted. Okay, so this is the duty cycle of this now the signal. So suppose this is T1 and this thing is T. Okay, so now this thing is 9.5. Okay, okay, so now this thing is 9.5, but earlier it was 12 volt. So we can write over here 12 divided by 9 point, sorry, 9.5 is equal to, so this, sorry, so yeah, so this is nothing but T by 2, right? T by 2, and this is T1. So this will be T by 2 divided by T1. So T1 is equal to T by 2 into 9.5 divided by 12. So duty cycle D is equal to T1 divided by total time period T into 100%. That means now if we put T by 2 T into 9.5 divided by 12 into 100%. So T cancels out. That means this is 950 divided by 24. That was percent. So 950 divided by 24. This is near about 40%. So the correct answer will be 40%. Okay. Okay. The next question: what is the duty cycle if the wiper is in the bottom position? Bottom means it is connected over here. That means the entire resistance will appear. That means if it is minus, if it is plus, then the entire 2.2k will appear over here, and here it will be 3.3k, and here it is 10 volt, and here we are applying this sinusoidal voltage of plus 12 volt and minus 12 volt. Okay, so this is the VO. So now what is the V minus? V minus is nothing but 10 into 2.2 divided by 2.2 plus 3.2. Simple, the voltage divider rule, that is 10 into 2.2 divided by 5.5. So 2, this is 5, this cancels out, so this is 4 volt. So now this VO will be AOL V plus minus V minus, that is AOL V plus is V plus minus 4. So minus 4 means now it will be 8 volt. So 8, and it is minus 4, this means minus 16 to 8 volt. Okay, so this is the thing, that is the 8 volt. So if we consider in the similarly like in the previous question, if we consider this as T1, so 12 divided by 8 is equal to T by 2. Earlier it was T by 2 and it was T1. So T1 is nothing but T by 2 into 8 by 12, right? So the duty cycle is T1 divided by total time period T into 100%. That means T by 2 into 8 divided by 12 into T into 100%. So T cancels out. So it will be 800 divided by 24%. So 800 divided by 24, it is 33.33. 33.33%. So the correct option will be 33%. So it will be 33%. Okay. Yeah. So as we have done earlier also, the same thing. So it was previously it was t by 2 and here it was t1. So you can write like that. Okay. Yeah. So the next question. In the circuit shown in the figure, what is the value of VO? Okay. So this is also a negative feedback system. So V plus and V minus will be equal, and V plus is connected to ground. So this is also connected to ground, virtually ground condition. So the current flowing through this terminal is nothing but 2 divided by 4.7 milliampere, and the same amount of current will flow through this, because here the current will be the current flow in this op amp will be 0. So this VO will be nothing but V minus of 1.2 k into 2 divided by 4.7, and now V minus is nothing but 0 minus 1.2 divided by 2 divided by 4.7 equal to minus 2.4 by 4.7. So 2.4 divided by 4.7 is nothing but minus 0.51 volt. So this will be the correct answer. So you have to simply apply the KCL to get the question solved. Okay. Okay. So this is the last question. So in the same circuit, what is the value of I1? So see one thing. So this terminal is connected to ground, and now you got the VO value. VO is minus 0.51. So VO is minus 0.51 minus 0.51. So now if we apply KCL at this node, so 0, because it is grounded, 0 minus of minus 0.51 divided by 1.2, this is this resistance, the current flowing through this, plus I1, that is the current entering through this node, is equal to minus 0.51 divided by 2k, that is the current flowing in this term. So you can write out 0.51 divided by 1.2 plus I1 is nothing but minus 0.51 divided by 2. So I1 is nothing but minus 0.51 divided by 2 minus 0.51 divided by 1.2 equal to minus 0.51. If we take common, 1 by 2 plus 1 divided by 1.2. So it will be 1 divided by 2 plus 1 divided by 1.2. So it will be minus 0.51 into 1.333. So if you multiply with this minus this thing, it will come out minus 0.68 milliampere. So it will be minus 0.68 milliampere. So this I1 will be nothing but minus 0.68 milliampere. Okay. So that's all for today. So if you have any doubt or any question related to this, you can post the doubt in the discussion forum, or also you can ask me in the next tutorial class. So okay. Uh, so we'll meet again on the next Tuesday from 6 p.m. to 8 p.m. Thank you.